device in history.
Elliptic curve cryptography, that is. This system of encryption is revolutionizing internet security. It is used to secure some of the most elite entities in the world, such as Bitcoin, big-name companies like Google and Facebook, and even the NSA. Suggested in 1985 by Neil Koblitz and Victor Miller, elliptic curve cryptography is the best encryption system in the world. And despite 30 years of trying, mathematicians are still unable to break it. In elliptic curve cryptography, data is encrypted with a public key and decrypted with a private key by plugging these keys into an elliptic curve function. These keys are just incredibly large numbers in the quintillions, which makes guessing them impossible. For example, you would have a higher likelihood of guessing the star I'm thinking of among 900 trillion universes than you would of guessing a private key. So why elliptic curves? 3 reasons make elliptic curves ideal functions for generating these keys. First, they're fantastic trapdoor functions. Second, they're symmetric about the x-axis. Third, any non-vertical line connecting any 2 points will always intersect only one other point. So how are these properties used to generate keys? First off, the trapdoor property enables us to easily generate a number, but makes it extremely difficult to solve for that number. For example, say you were playing billiards and you hit the cue ball n number of times. If someone walked into the room after you hit the ball n times, they would not be able to figure out n, even if they were given the starting and finishing positions. The next properties show us how that number n is calculated using elliptic curves. Because a line connecting 2 points will always intersect a third point in the graph, we can find that third point given the first 2. This point can then be reflected over the x-axis to form a new point. A line connecting that point with the point we started with will give us another third point. That point can then be reflected over the x-axis, and we can repeat this process however many times we want. We then restrict the domain and range we are working with by setting a maximum that, when a value crosses it, that value wraps around to 0 like the numbers on a clock. This number is set to an enormously large prime number. This diagram shows what a graph of an elliptic curve becomes once this process is done. In Bitcoin, only whole numbers are used, and the maximum is set to an enormous prime number. Using this approach, we can set up a crypto system. We define it with 3 main parameters: the maximum, the equation for the curve, and the starting point. The private key is a random number a, and the public key is the starting point dotted with itself a times. Solving for the private key given the public key is called the discrete logarithm problem, and it's the ideal trapdoor function needed to create a secure and fast cryptography system. This system is so effective that in order to break a 228-bit key, you would need computing power so massive that the energy used to power it would boil all of the water on Earth. This security and speed makes it ideal for keeping secrets and for making the entire world a safer and more secure place.